Now, I would like share some advanced topics of nanotechnology by focusing on the graphene nanophotonics. Basically, graphene is fascinating carbonaceous two-dimensional nanomaterials as introduced in the lecture 2. It has very high carrier mobility. It is also mechanically very strong. It is very thin with atomistic thickness. In addition, it has very high thermal conductivity. In terms of nanoelectronics and nanophotonics, it is important to understand the fundamental aspect of the electronic structures of graphene. In principle, as shown in the left figures, graphene is zero bandgap material. This means that there exists a linear dispersion in the vicinity of the K points. The valence band is filled, while conduction band is empty. The electronic structure of graphene can be electrically or chemically doped. As shown in the right figure, graphene has peculiar chemical and molecular structures with sigma bonds via sp2 orbitals. This structure provides strong binding. In the graphene, pi bonds via p sub z orbitals determine electrical and optical properties. However, there is no interaction between sp2 and pz by symmetry. Graphene lattice can be viewed as sum of two sublattices A and B whose wave functions enter solution of tight binding Hamiltonian as bases. In terms of photonics, graphene is very interesting. Graphene's conductivity determines to a large extent surface plasmon polariton dispersion properties and losses in the structure. Due to nearly constant conductivity for intrinsic graphene, there is sharp cutoff for the interband absorption below the Fermi energy. In addition, there exists phonon energy threshold at 0.2 electron volt as shown in the upper right figure. Graphene is a basically broadband saturable absorber. This is based on poly-blocking of interband transitions. In addition, graphene has large third-order susceptibility. This is due mainly to resonant transitions leads to efficient harmonic generation, four-wave mixing, and so on. However, for graphene flakes, these optical properties are limited due to geometrical limitations-driven modification of the electronic structures, topological defects, edge effects, and so on. Graphene's advanced photonic properties are advantageous in constructing waveguide for surface plasmon polariton with long lifetime. By spatially varying Fermi energy, we can fabricate artificial structure with periodically changing conductivity. Then, surface plasmon polariton can be reflected in the Fresnel-like fashion from the boundaries between the different conductivity regions. In particular, graphene photonics is advantageous for broadband spectrum ranging from visible to infrared from 514 to 2400 nanometers. Typically, in this spectrum, we need metallic fingers due to limited current generation as shown in the left, middle, and right figures. For example, for the graphene-based photodetectors, error-free detection in the optical carrier frequencies have been demonstrated with 10 gigabit per second link at the telecommunication wavelength at 1550 nanometers wavelength. To construct the graphene-based modulator,
Yep.
tuning Fermi level is important. For this, we can take advantage of interband transition in graphene with a threshold as a switching mechanism like optical switch. Graphene-based modulators have different forms. For example, for waveguide integrated graphene-based electroabsorption modulator, the modulation can be done by actively tuning Fermi level of monolayer graphene. For this structure, 250 nanometers wide silicon waveguide is connected with 50 nanometers silicon to 1O electrode. 7 nanometers dielectric spacer, followed by mechanically transferred graphene sheet. Counter electrode connected with PT as shown in the upper left figure. Another structure is based on the combination of silicon ring resonator coupled with RIP-type silicon waveguide as shown in the upper right figure. Similar structure can be prepared by combining graphene disc on gallium arsenide coupled with optical fiber with tapered shape as shown in the lower left figure. Finally, we can stake three-dimensional structure with multilayered graphene and dielectric layers forming quantum well as shown in the lower right figure. In terms of plasmonics, graphene is also very fascinating material. Surface plasmon polariton suffers damping in graphene at mid-infrared spectrum. For example, graphene ribbons work as tunable metamaterials. This structure can make plasmon hybridization. In addition, due to its atomistic thickness, it works as a monolayer atomic cloak. In the graphene nanoribbon structure, wave vector mismatch impedes direct excitation of surface plasmon polaritons. This is advantageous in achieving efficient resonant coupling. Therefore, surface plasmon polariton wavelength is changing depending on applied bias voltage, for example Fermi energy. In the regime of small losses, the wavelength of the surface plasmon polariton is proportional to Fermi energy. When with the high degree of confinement, the wavelength of the surface plasmon polariton is about 1 or 2/100th of the incident light wavelength. Using graphene, one can construct some advanced photonic devices. For example, as shown in this figure, plasmonic antenna can be fabricated in the form of sandwich between two monolayers of graphene. In here, antenna contributes to enhancement of photocurrent through transfer of hot electron generated in the antenna structure upon plasmon decay. On the right, you can find electrical transport characteristics of the device. As can be seen from the plot, drain bias 1 MV band crossing energy at the Dirac point reached at peak resistivity at gate voltage about 30 volt. Graphene supported hot electrons contribution to photocurrent is an example of field enhancement. This can be observed by direct excitation effects calculated from FDTD simulation. The smaller the antenna size, the higher the internal quantum efficiency, IQE, of the photodetector. Therefore, we can expect a good performance of the photodetectors by combining graphene with antennas extends optical sensitivity. There are problems for graphene photodetectors such as low light absorption, difficulty of extracting photoelectrons, and absence of photocurrent for uniform illumination. Voltage current produced in two terminals will be in opposite polarity. To solve these problems, one can use plasmonic nanostructures near contacts incident light converted to plasmonic oscillation by enhancing the local electric field. Due to advanced photonic properties of graphene at telecommunication frequency and terahertz range, we can have some perspectives on the graphene nanophotonics targeting integrated optical circuit as illustrated in this figure. As shown in the figure, graphene can work for the model-locked laser with ring cavity. In addition, graphene can be used for optical modulator as well as photodetectors, which will provide separated signal to be combined at the beam combiner. For future information processing devices, optical integrated circuit is one of the most promising strategy, and therefore, graphene would attract increasing research interest in the fabrication of a variety of optical modules. Now, I would like to introduce some advanced technology to control nanomaterials. In the era of nanotechnology, it is important to manipulate and control nanoparticles. Nanotweezer is nanoscale tweezer with a pair of long nanotubes on the surface of metallic microtip. Using the nanotweezer, mechanical manipulation and interrogation of polystyrene nanoclusters can be done in nanoscale down to the 500 nanometers. However, nanotweezers can have problems in releasing the nanostructures when opened dominance of van der Waals force and electrostatic forces. Measurement of radiation pressure using light sources and a torsion balance. Indeed, English physicist Poynting said a very short experience in attempting to measure these forces is sufficient to make one realize their extreme minuteness, a minuteness which appears to put them beyond consideration in terrestrial affairs. Observation of optical scattering and gradient forces decoupling thermal effects. First optical tweezer, tightly focused beam of light holding particles in 3 dimensions. Basically, optical nanotweezers is applied for the Rayleigh regime, in which the particle's size is sufficiently smaller than the wavelength of incident light. In this regime, we can think of the gradient force, which is the electric dipole interaction that scales down with particle volume. Brownian motion from thermal fluctuations may be large enough to overcome the trapping forces at the nanoscale. For stronger gradient force, alternative trapping geometry such as counter-propagating beams as shown in the upper middle figure. Gradient force from tightly focused laser beam can hold particles in all 3 dimensions, which minimized spatial fluctuations. For larger trapping volume, alternative particle geometry such as nanowires can be tested as shown in the lower middle figure. We can think of the plasmonic antennas such as identical metal structures with nano gap. This is basically nanograding. In this structure, capacitive effect leads to an intense hot spot. The hot spots can hold the particles in the focusing area with minimized spatial fluctuations. However, there exists drawback for the plasmonic nanoantenna-based optical nanotweezers, such as heating from the plasmonic nanostructures to high temperature can give irreversible damages to the sample, in particular, organic or biological samples. In addition, there would be some problems for the materials with thermo-optical properties, in which refractive index varies with temperature. There are several notable applications of the optical nanotweezers. First, using power spectral density obtained from the optical nanotweezers, we can detect or quantitatively measure trap stiffness as shown in the upper left plot. Second, for biological applications, measurement biological molecules' structural transformation can be done. For example, we can use the optical nanotweezer to measure RNA hairpin undergoing conformational transitions as shown in the lower left plot. When the nanomaterials are levitated, we can apply crossing optical field to obtain more detailed information. For example, torsional motion of non-spherical nanoparticles can be measured as shown in the middle figure. This indicates that the optical nanotweezer can be a good tool for the optomechanics. Ultrasensitive torque measurements may be achieved with laser cooling. Another cool example of the application of optical nanotweezer is laser cooling of nanoparticles as shown in the rightmost figure. Finally, let's review some critical issues on the nanoparticles for people and other biological systems. Especially, it is an important issue for researchers who frequently use and test the nanomaterials. Therefore, please focus on the contents in following slides. Basically, nanoparticles can be very dangerous for the biological systems due to their large surface-to-volume ratio. The larger the ratio, more effective the interactions or reactions. Risk is a product of the exposure rate and the material's toxicity. Therefore, it is not surprising that the nanoparticles from combustion and industrial processes or from volcanic eruptions have long been critical health issues for respiratory problems. There are a variety of diseases associated to nanoparticles exposure, such as Crohn's disease, colon cancer, dermatitis, vasculitis, podoconiosis, and so on. In particular, gaseous phase nanoparticles in the form of Hume can be easily inhaled into the body, and the particles can reach the brain, lungs, circulatory system, heart, and other organs. In the scale of cells, nanoparticles can be easily internalized in the cells by interacting with mitochondrion, nucleus, cytoplasm, membrane, and lipid vesicles. In subcellular scale, nanoparticles can affect biological behavior such as lipid peroxidation, plasma membrane damage, genotoxicity, inflammation, protein dematurization, apoptosis, and so on. Let's look at some specific case. Silver nanoparticles can easily penetrate cells and tissue. As shown in the left figure, silver nanoparticles can be dissociated into silver ions. The silver ions in the lysosome can suffer oxidation. Via cysteine, silver ion can be silver sulfide, which will affect the mitochondrion to suffer premature apoptosis. As shown in the right figure, metallic nanoparticles can reach deep inside the lungs such as alveoli and bronchiole. When over threshold, metallic nanoparticles can induce critical respiratory issues. Human immune cells or macrophages are organized when they cannot get rid of a substance such as tuberculosis, leprosis bacteria, and asbestos. This is called as granuloma. Abnormal granuloma can induce frustrated phagocytosis, and even cancer of the mesothelium, which is a protective sac that covers most of the body's internal organs. Aggregation of nanoparticles inside the body make potential risk. For example, for the carbon nanotubes inhaled, the subpleural tissue of mice with does if 1 mg per cubic meters to 30 mg per cubic meters. Formation of mononuclear cell aggregates, immune reactions. CNT introduced in the abdominal cavity of mice show asbestos pathogenicity/protein corona, defines the biological identity of the particle. Please refer to detailed information in the URL attached in this slide. Now I would like to express my sincere gratitude to your concentration and attendance in these lecture series. I wish for your successful career in your research and development for nanotechnology.